All right, so we are on page 35 of your note packet, advanced equation solving, something like that it's called. Some of the P's came out, or the pies came out as P's again, and some of those little question marks are floating around, so just ignore those. So we're going to build on the skills we learned last time of some more basic equation solving skills, finding the exact values. So at the ends of these questions, I'm going to go quickly through them. I'm going to assume you feel okay about that. If not, those are things we can talk about in class together next time. So, question number one, I kind of gave you the hint about where I wanted you to start with it, but we can use our known identities to now help us solve trig equations. So first of all, let's see this first question: sine 2x equals cosine x. Let's see here. All right. So what we can't do is we can't just divide by 2, right? This is different from 2 sine x. All right, my board just froze. There we go. All right, so this is different from 2 sine x. So we can't just do that. We could probably just use our common sense and kind of reason our way through this, maybe make a little table of values, and we could probably just guess and check this thing. But I do want to show you how to solve it algebraically. But hopefully what we do see is that this sine 2x is our double angle identity for 2 sine x cos x. So we can expand that and turn it into this. So now we're making some progress. Now we're getting somewhere. We mentioned this last class, but if I have an equation that looks like this, like x squared equals x, I cannot just divide out by x to get my solution, right? We will be losing track of a possible answer. So we can't do this. We can't just divide by cosine in this case. But hopefully what we remember from last time is that a really, really important first step for a lot of these is to use our zero product rule. So what I can do is subtract cos x from both sides. Careful, those are not like terms. So now we're here. So now we're making progress. It looks like we're getting closer to a solution. At this point, I can factor out a cosine x term, and I'm just left with 2 sine x minus 1 equals 0. And now it's really just exactly what we looked at last time. Now I can split this up into the two different equations that equal 0. So for this to work, either cosine x has to equal 0 or 2 sine x minus 1 has to equal 0. We can quickly solve that to be sine x equals 1/2. And this is what I mean. I'm not going to go through the whole unit circle, the special right triangles. However you kind of got good at this last class, we're just going to continue doing the same thing. So my answers, I know when cosine of x is equal to 0, x would have to either be pi over 2, or 3 pi over 2. And then sine of x is a positive 1/2. So quadrants 1 and 2 with a reference angle of pi over 6. So there would be my two sine values where the ratio of the sides is 1 over 2. All right, so nothing crazy, nothing totally new, but we will need to kind of continue to think about our identities. Next question. I kind of gave you a hint about where I wanted you to start with this one. But we can also use our Pythagorean identities to our advantage when we're solving these equations. So same thing as above. We could probably make a little table. We could probably just reason our way through this and guess and check and find the values that make this work. But in this case, we can solve it algebraically. We can kind of make sure we know what we're doing. So let's see. There's no like terms. I don't see any factoring. I don't see any reciprocals. So I kind of gave you the idea of where to start with this one. But introducing Pythagorean identities into our equations is sometimes a really helpful way to at least get something going, to maneuver something, to change something, to at least get going on the right track. So that's what I'm going to do. Remember, this isn't an identity. I don't have to only work with one side at a time, right? So I don't have to only multiply or divide by 1. As long as I do something to one side of my equation, I can do it to the other side. One side note, one thing to be careful of. Think back to the beginning of the year. We were doing some equation solving with things like this, with radicals. If If I have x equals 3, if I tell you that's a given, that x is 3, I could square both sides. I'm not breaking any rules. That would keep my equation intact. And I would get x equals 9. X squared equals 9. Why is my board not working again? Come on. All right, I'm gonna have to pause and restart this. Let's see, are you gonna come back? Doesn't look that way. All right, I'll be back in a second. All right, let's try this again. So all right, there we go. If I were to square both sides, I would get x squared equals 9, which is still true. It still works with my first equation. But if I then wanted to square root and get back to an x equals, remember there's two ways to get 9 if you're square rooting. And I could start with +3 or a -3, right? I could square 3 to get 9. I could square -3 to get 9. But we know from my original statement that x is 3. X is not -3. So I would have to reject that extraneous negative solution. So when you are squaring both sides of an equation, any equation, you always need to make sure to check for extraneous solutions. So that's just something to keep in mind when we get to the end of this one. So let's do the math. Let's expand. So cosine x plus 1 times cosine x plus 1. We have cosine squared x. Careful here. Don't forget that term. Okay. So let's see. Still no like terms. Still nothing I see that jumps out at me, but we can use this Pythagorean identity that we just created to get ourselves all cosine terms in this function, in this equation. So that's a potential first step. So now, okay, I have some cosine squareds, I have some cosines to the firsts, I have some constants. So that is my cue to solve it like a quadratic to get everything equal to 0. So I'm going to add cos squared to both sides, and I'm going to subtract 1 from both sides, and we actually end up with a pretty straightforward equation. The 1's just subtract out to a 0, so I'm left here. All right, at this point, I have a GCF. And it goes back to what we learned last class. So 2 cos x equals 0. So I know that tells me that cosine of x has to equal 0. It also tells me that cosine of x has to equal -1. So there's a few different possibilities here. So my x value, so when is the cosine equal to 0? Cosine is equal to 0 at pi over 2 and 3 pi over 2. Cosine is -1 at pi. So there's my 3 possible solutions. All right, but like I said, we need to go back in and check for extraneous. So if I take that pi over 2 and I go back up to my original equation and I plug in, whoops, I'm jumping the gun there a little bit, and I plug in pi over 2. Cosine of pi over 2 is 0. 0 plus 1 is 1. Sine of pi over 2 is also 1. Pi over 2 checks as a solution. Let's try 3 pi over 2. Cosine of 3 pi over 2 is 0 again. 0 plus 1 is 1. That looks good. Uh-oh, I can kind of see what's coming here. Sine of 3 pi over 2 is -1. So 1 does not equal -1. We have to reject this solution. But it's kind of neat to see why that would work. If I were to apply the square to both sides, I would get 1 equals 1, which would work. So that's why squaring these equations like this does throw that possible extraneous into your answer. All right, and then pi does work. I'll give you that one for free. So yeah, next class, we're gonna have a lot of time to practice just these more advanced equations. I think you'll have some fun with them. Other than that, that's all I got. I'll see you next time. Bye.